So, buongiorno go fast. So this is actually the only Italian word I remember. So this is the last deep dive session in GoLab. Thank you for coming. My name is Takuto Nagami, and I'm joining this conference from Japan. I'm currently a student at Chiba Institute of Technology, where I'm studying computer science and network science. Today, I discuss how to resize animated GIFs using pure Go. So specifically, when I say resize, I mean scaling the GIF in and out. It's about adjusting its visual dimensions, not file sizes. So let's take a moment to think about why we might need to resize animated GIFs in the first place. So how many of you have had GIF resizing in your product or your services? Can you raise your hand? Thank you. So, and how many of you have actually implemented GIF resizing by yourself? So as you can see, it's relatively rare use case, actually. For me, it came up when I was working on animated icons and animated stamps for social networking services. So this is Track, an internal messenger application at Trap. Trap is a CS student community in the university, and I have been actively involved in for years. So during that time, I had an opportunity to act as a backend maintainer of this Track. So Track is inspired by Slack, but specified to your needs. So its most mind-blowing feature is a hierarchical channels, like a channel tree, so allowing us to categorize discussions more effectively. So this structure helps us organize various topics and projects within a community. And in Track, we have animated icons and stamps, like this. So icons allow users to express themselves more creatively and with more individuality. And stamps make communication more fun, like this, and lively, creating a more engaging experience for Track users. So when it comes to the sizes of these images, the size of the icon is 256 pixels by 256 pixels, and that for the stamp is 128 pixels by 128 pixels. So anything larger than that just doesn't make sense. It's redundant. So, and additionally, resizing the images also reduces the file size, which is important for a few reasons. First, we don't have money since we are a student community. So we don't have much money to invest in storage, so managing image size is essential. And moreover, we need fast response times, so especially in a chat application where performance is a key. So resizing the GIF images is the most efficient approach, almost necessary actually, to support this feature. So how do we resize GIF using PureGo? Well, it turns out there isn't a lot of information available about this. So Go standard libraries, and even its sub-repositories, I mean golang.org X libraries, don't offer built-in support for resizing GIF images. While Go does support single image formats like JPG or PNG, it doesn't natively handle animated GIF images. So there aren't many, and moreover, there aren't any major third-party libraries that offer a pure Go solution either. As for now, the default standard for working with GIFs in Go typically relies on CLI tools or CGO bindings to C-based image processing libraries. So currently, there are a few common solutions for resizing GIFs like that. So the first one, ImageMagick, is an open source C image processing tool with a CLI. So we actually used ImageMagick in Track for GIF resizing. And Magic Wand, next one, is a C library for image processing that serves as a core of ImageMagick. It provides a more programmatic API compared to the CLI version of ImageMagick. And another C version image processing library is libvips. So this one has an officially recommended CGO binding for Go developers, so it's helpful. So these choices are common because they are matured and highly capable. They can process most image types correctly and effectively. While these solutions offer some functionality, they also come with drawbacks. First, security issues arise, especially when using the command line interface from the code. So this can open the door to the code injection or arbitrarily execution risks. Although CGO provides a somewhat safer alternative, it still doesn't match the safety of pure Go. Additionally, these libraries often bring in a lot of extra baggage. Most are built to handle extensive image processing, resulting in large data sizes and redundant codes. And this makes them unsuitable for application containers recently. Moreover, I wanted to migrate the base image to the distilless image for better security and simplicity. But particularly when using distilless image, handling C dynamic libraries for the ImageMagick or so for image processing is terrible. So today, let's tackle resizing animated GIFs using only pure Go, ideally just with Go's standard libraries and subrepositories. So let's take a look at what exactly is a GIF image. So as you know, essentially, a GIF is an animated image, not a video or a multimedia file. So its graphic format is a graphic format that can display animation in a loop, like this. Unlike more complex videos like MP4, GIFs are simple images, making them lightweight and easy to share online. To give you an example, here's a fun GIF of a cow eating grasses, like that. Let's break them up. So it's made up of multiple frames, which are individual images. So when they are displayed in a sequence, they create a movement. So these frames loop continuously, forming the full animated image you see. So from now on, I call these individual pictures frames, and the whole data image. There's the word. So what's actually contained in the GIF image? So let's take a look at the whole image first. So the image size, the width and height, refers to the overall dimensions of GIF, including its width and height. The global color palette is a set of up to 256 colors that are available for the entire image. As for each frame, they clearly have image data. Of course, the delay specifies the amount of time each frame is displayed. The color palette is also in each frame, allowing them to use its own set of colors. The disposal, which will be significant later, is also contained in each frame. So these elements together create a GIF image. Next, let's take a look at the existing image processing features that Go already provides. So first, let's take a look at the Go's image GIF package, which is a part of the standard library. So this package allows us to decode GIF images into struct. So the function GIF decode all decodes the entire GIF image binary and returns a GIF.GIF struct, which contains all the necessary data for GIF images. So inside this struct, the image holds a slice of image paletted, which represents the individual frames of GIF. So the delay field specifies the delay for each frame, since it is slice. The disposal field specifies the disposal for each frame. And the config field contains the GIF's width, height, and global color palette data. So with this built-in structure, Go provides the fundamental tools to work with animated GIFs. Next, let's explore GoLab.org X image draw package, one of Go's sub-repositories that extends the functionality of image manipulation. So the draw function allows you to draw one image onto another. So the function uses an alpha compositioning operator called OP there, which determines how the source image is combined with the destination image. So the draw source operator, one on two, completely replaces the destination image with a source image. On the other hand, the draw over operator simply overwrites the destination image with a source, maintaining the destination's pixels under the source's transparent pixels. And additionally, the GoLab the orgx image draw package provides the draw scalar interface, which is essential for resizing images. So the draw scalar interface allows you to resize single image to a specified size. So by implementing this interface, any kind of struct can resize images, so which can be crucial when working with GIFs, especially when you scale individual frames. And draw package has a struct that implements this interface. With these types and functions from the image GIF and GoLab the orgx image draw packages, we can implement the simplest GIF resizing solution. So first, we need to create a GIF.GIF struct to hold a destination GIF image. As you see, we create a container, that slice, for the resized frames in image field. So this field will hold a slice of image, the paletted, to store the resized frames. So for other properties, we copy them from the original source GIF, such as delay, disposal, or config fields. And then we use a for loop to iterate over each frame of original source GIF. So in each iteration, we retrieve the original frame, SRC frame, and resize that using the draw scalar interface, for example, with a Catmull ROM kernel as an example. So after resizing here, we append the resized frame into image field of a new GIF.GIF struct, like this. So in this way, simple GIF resizing could be done. However, there are some traps when it comes to resizing any kinds of GIF. So some GIF images have features that or simple implementation, as we see here, can't handle properly. So these features can cause issues that we need to address to ensure the resized GIF work as expected. So actually, this is the main purpose of this session. So highlighting these traps and providing solutions for how we can deal with most GIF images. So let's explore these challenges and look at the ways to handle them. Trap 1, optimized GIF animation. So let me show you an example GIF animation. So this GIF features Hatsune Miku, as you know, a famous character in Japan. As you can see, she's blinking in this animation. She's cute, isn't she? So let's resize the GIF image to the same size. However, as you can see, a problem occurs. Oh no, sadly, she becomes long. Oh God. And it's long, and it seems to be wrong, right? So this distortion happens because of the delta frame optimization. In optimized GIF images, instead of storing the entire image for each frame, as you can see in the left, only the area that changes from the previous frame is stored, as you can see in the right. So this means that each frame contains only the image data for the changed area, along with the position data for where the change occurs. So in this animation, Hatsune Miku is blinking, but notice that certain parts of image don't change. Her body, her hair, and the background remain static throughout the animation, right? So as you can see in the picture on the right, the only part that changes is her face, the area around her eyes. So if we simply resize all the frames to the desired size, here's what happens. Frame 1 is fine, because the first frame always has its full image data, including all the details for the face, body, and background. However, for frame 2 and beyond, the delta frame optimization causes issues. Since only the image of the face is stored, resizing causes the frame to stretch out, distorting the image. As you can see here, the code we looked at before, we bound the size of the resized image to the destination image size, not a frame size. So that is a problem. Well, that's why mix stretched out. So how can we solve this? The key to fixing this issue is calculating each destination frame size correctly. So this is additional code we need to implement that. So first, we calculate the ratio between the original size and the desired size, right? So next, we calculate the destination frame bounds in the middle. So using the ratio we calculated, we determine the new size of each frame based on the original frame's dimensions, so ensuring that the resized frame fits correctly. So finally, we resize the frame using the bound, as you can see here. So with the frame size calculation, the problem is resolved. So frame 1 remains unaffected as it still contains the full image data just like before. And happily, frame 2 and beyond now becomes correct. So with the frame size calculation, the problem has been solved. Hooray. However, another trap comes up. So let's take a look at the next issue that arises when resizing GIFs. So trap 2 is interpolation. So let me show you an example to illustrate the issue. This is a para-para.gif. It's designed in a style similar to the manga, where each frame gives the appearance of movement through a series of static images. So in this animation, a person runs toward us, hit the wall, and cracks appear on the screen, as you see. And let's take a look at the result after resizing the para-para.gif. So as you can see, black jaggy noises appears, as you can see, like this. So particularly in the horizontal direction. So you should think, what are these black jaggy noises? Well, let me explain. To solve this issue, we need little knowledge about interpolation. So let's dive into the abstract concept of interpolation. So interpolation is a process of mixing pixel colors to estimate new pixel values when resizing an image. You see? So to determine how pixels should be mixed, we use a kernel, which is essentially a function that guides this mixing process. So common interpolation kernels include bicubic, Lanczos 2, and Lanczos 3 or so. And these kernels vary in how they calculate the new pixel values, with some offering smoother transitions and others offering sharpness. And however, when mixing transparent and non-transparent pixels sometimes leads to unwanted noise. So it seems that the noise specifically happens when image contains a transparent pixels. The investigation is still in progress, actually. So, but I suspect that how the transparency is handled during the interpolation is contributing to this problem. So possibly someday I will try fixing this, but not the near future. But here's a workaround. So it's piling up the frames before resizing. Now, this approach might be a bit hard to imagine at first. So let me explain how it works. So here, there are transparent pixels in the GIF. Like, it's black. So what we want to do is get the transparent pixels out of our mind, meaning we want to focus only on non-transparent pixels while resizing, right? So now let's see how GIFs are rendered here. So we render them by piling up the frames, right? So to render the current frame, we take a current frame to pile it up with a previously rendered frame. So now, the previously rendered frame is already a combination of all the frames piled up until that point, starting from the very first frame. So this way, each frame builds upon a previous one, right? And until now, we've been focusing only on resizing the current frame, right? But what if we resize the rendered current frame instead? So by simulating the rendering process and resizing the entire rendered frame, which includes the piled up frames, we can avoid handling the transparent pixel directly. So here's the code for this approach. First, we prepare a canvas for rendering called temp canvas here that will hold entire rendered frames. The size of this canvas is the same as the source image, as you can see. And in the for loop, we pile up the current frame onto canvas using the draw function. So we use a draw over operator to ensure that each frame is drawn on top of the previous one, preserving the previous frames while adding the current one. So this builds up the rendered frames step by step. And after piling up frames with draw function, we resize the current canvas just like we did before. And finally, we need to trim the frame to account for delta frame optimization we see before. So using the draw function again, we pass the calculated destination frame size, which ensures that only the relevant part of the frame is included in the final image. So finally, after trimming and resizing, we append the resized and trimmed frames to the destination GIFs. It seems like we're almost done, but the problem still remains in some cases, some corner cases. So this noise can be solved by piling up frames if the image has non-transparent background. However, for images with transparent backgrounds, like this, the issue can be fully addressed with a workaround. So ultimately, I guess that this problem we will need a fix in the resizing algorithm within a draw the scalar interface, or draw the scalar structs that implements a draw the scalar interface. So as I mentioned before, the investigation is still in progress, and I'm working on finding a solution. But the problem remains in the images with transparent background, sadly. While the issue is partially solved, another trap appears. So this new problem is caused by implementation of simulating the GIF rendering process. So although the workaround we see before helped with the noise, helped with the black jaggy noise, it introduced new challenges that we need to address in the next steps. So the next trap we need to see is a disposal. So let's talk about a disposal, which is also known as frame disposal methods. So disposal determines how each frame should be treated after rendering. So there are three types of disposal methods. One's known, one's background, and one's previous. So the first one is a disposal none. So this method means doing nothing after rendering the frame. So this process simply moves on to the rendering of the next frame without modifying the current frame, as you see in the GIF image, in the example GIF images here. And the next one is a disposal background. This method overrides the area of the frame with a background color after rendering. So it ensures that any areas of frame are replaced with a background color. You can see the exact rendering process here. And the last one is a disposal previous. This method deletes the current frame before rendering the next frame. Essentially, it rolls back to the previous frame, restoring the state as it was before the current frame was rendered. As you can see, each frame disappears before the next frame is rendered. And inappropriate disposal processing can cause problems like this. So as you can see with the cute frog GIF here, all the frames remain instead of being properly disposed of. So leading a messy and distorted animation like you can see here. So this happens when the disposal method is not applied correctly. So particularly with transparent backgrounds. To fix this, we need to ensure that the disposal method is applied correctly. So let's implement that. So here's the code for processing disposal correctly. So first, prepare a uniform image of a background color in the top. So background color is picked up from the global color palette. And this image will be used to fill the frame areas when necessary, like disposal background, ensuring the consistent background color. Next, copy the temp canvas into a previous variable. So this creates a reference of a previously rendered frame for disposal previous. So then, after the resizing, use a switch statement to handle disposal based on the frame's disposal method. So when the disposal method is none, just nothing. And when the disposal method is background, replace the source frame area with a background color image on the temp canvas using the draw function and the draw source operator here. This will fill the frame with a background color. And when the disposal method is previous, replace the entire temp canvas with a previous frame similarly to the background method, like this using draw function. So this restores the previous frame to the canvas, and that's it. So by following these steps, the disposal will be processed properly. Let's go. And we can now avoid issues with transparent background images and frame rendering. So, however, we have a few more things to work on. So first, we want the option to retain the aspect ratio of the original image. Next, we want to make the resizing kernels selectable, allowing the users to choose different resizing kernels, such as bicubic or Lanchos, will provide more flexibility and control over the resizing quality. Lastly, we want to make it concurrent to improve performance, especially when dealing with large size of GIFs. We could implement concurrent processing, significantly speeding up the resizing process. And here's a solution. Wow. With the knowledge I presented today, I've created my original GIF resizing library, ResizeGIF. So this library includes the basic functionality for resizing GIFs, as well as some additional features in the previous slide. Hooray! I highly recommend considering this library when you need to resize GIF images in your projects. And please give me some feedback. Now, let's compare the performance and quality of ImageMagick CLI with my ResizeGIF library. So in this experiment, we'll compare the performance of ImageMagick CLI and ResizeGIF for resizing GIF image from 512 pixel by 320 pixel to 256 pixels by 160 pixels. Right? It's a half of the size. So for ImageMagick CLI, we use the following command to resize the image. You can see here. So magic filter Lanchos scale 50%. And for CLI using ResizeGIF, I created that. And we measure the performance for single thread and concurrent version. So for all of these methods, I use the Lanchos 3 resizing kernel, which matches the kernel used by ImageMagick CLI by default to ensure an apples-to-apples comparison, right? And to evaluate the performance of each method, we measure the following metrics. First, we monitored the maximum CPU utilization during the resizing process using the top command. We also tracked the maximum memory usage during the resizing process using the top command. So, and most importantly, this is where we all want to know to measure how long each method took. We use the time command. The results were averaged over 5 trials to ensure accuracy and consistency in the comparison. So let's take a look at the result. So as we can see, ResizeGIF handled this pretty well. And the ResizeGIF looks almost identical to the ImageMagick one, as you can see. Interestingly, the image size generated by ResizeGIF is lower compared to the ImageMagick, actually. Even though both methods produce similar visual results. And here, as for the performance result, so let's take a look at the resize GIF with the single thread first. So for CPU, it used a little bit more percentage at maximum compared to the ImageMagick. The memory usage and processing time were almost the same as the ImageMagick one. So next, take a look at the resize GIF with a concurrent processing one. So the CPU usage increased by about 8 times due to the use of concurrent processing. So it depicts that resize GIF used CPU efficiently, right? The memory usage remained same, and the processing time was reduced to about 1/4 of the time taken by the ImageMagick approach, making it significantly faster. So resize GIF performs almost the same in terms of time for the same resources, and it becomes incredibly fast when running concurrently. When considering the comparison as a mature C program, so it seems pretty successful, doesn't it? It's successful. Hooray. Yeah. That works well. So as a side effect, after performing the two operations, deleting ImageMagick and migrating to the distroless base image, we observed a significant reduction in the Docker image size. So just as a reference value, so the image size shrunk from 201 megabyte to 64 megabyte, which is about 1/3 of the original image size. That is huge. So this size reduction is a great bonus as it makes the application more lightweight and efficient for deployment. So this is the end of the journey to resize animated GIFs only with pure Go. And then last, I would like to take a moment to express my gratitude to the following organization and people. So thank you, my university and my part-time workplace for covering most of my travel and hotel expenses. And I need to say thank you to these great people in the Japan Go community. And finally, a big thank you to all of you. Grazie. Thank you very much.
Thank you for your talk. Are there any questions? Yep.
Hi, thanks for your talk.
Thank you.
Just a question. What do you attribute the reduction of the size with Resizing compared to ImageMagick?
Sorry, can I hear again?
So in the results, you showed like the size of the not this one, but the actual GIF.
Actual GIF. Yes.
So here you saw, like, yeah, exactly. I mean, it's not a big difference, but I'm just curious, what, like, if you looked into why is it smaller?
Yeah, actually, I'm not. Yeah, I'm not clear about that actually, but this is just a result, so I don't know about why it shrinks down.
Sure, that's fine. Thanks.
Yeah, thank you.
Probably depends on the overhead that ImageMagick adds.
Yeah, yeah,
With respect to
yeah.
Oh, okay.
Actually, I don't know clearly about the ImageMagick algorithm to resize images. So
I use it too. That's why.
really.
Yeah.
Mm-hmm.
I personally don't know what ImageMagick adds in comparison to your library, but I think there is some overhead with respect to what you do because you work directly with the frames with respect to whatever ImageMagick does. So that's nice to see.
Yeah, thank you very much.
Then I work with GIFs as well because I like to draw some of the results of the programs that I create. And I showed it also in my talk previously. But yes, it's a nice tool to visualize what you are doing. So thank you very much.
Thank you.
Any other question? Yeah, sure.
I was wondering about when there was like the scaling that happened with the delta frame optimization. So does it? How is the image? Does the image have coordinates for the delta place? So how do you place it? It does have a coordinates.
Exactly.
Okay, yeah, because I was wondering, like, where does it place itself? Like, I thought there was just dimensions, but there are also position of the thing. Okay.
Yes, exactly. Thank you.
Thank you.
Any other question? Okay, that's it. Congrats.
Thank you very much.